Hey everybody, and welcome back to another video on my YouTube channel. For those of you who are new here, my name is Sid. I'm a high school senior who's really interested in computer science, anything computer science related really. On this YouTube channel I make videos about machine learning topics, competitive programming, theoretical computer science, and just general productivity, and any other topics that I might find interesting that are at least tangentially related to computer science or math. Today is a video. Today's video is part of my 66 Days of Data video series, in which I do 66 days of data science to learn data science again from the beginning with a different language than Python. I picked Julia, and it's really just to cement my skills as a data scientist and just make sure I understand the concepts that I've been using for so long. In my quest to learn Julia, I decided to play around with plotting because plotting is obviously a very important part of any data scientist's toolkit. And I've been learning Julia syntax for the past couple of days. Today I continued learning syntax and I learned to kind of use the plots library. And using the plots library, I plotted the movement of the double pendulum, which is a dynamic system that's used to show how chaos can be a thing. It's basically just one pendulum and then another pendulum attached to that pendulum, and then just moves around. Uh, I had to do this for my physics class anyways, so I decided to do it with Julia because we were supposed to do it with MATLAB and Simulink, but my MATLAB installation just kind of went weird, and then I had to uninstall it and reinstall it, and it's currently reinstalling, and that's going to take a few hours. So I decided to do it with Julia, and it was pretty simple to do, honestly. Solving differential equations with Julia is really easy, which is awesome, and yeah, it was really fun. The derivation for the formulas for the double pendulum, uh, I'll link in the description below. But basically, how a double pendulum works is, well, the equations of motion, not the motions of equation, but the equations of motion are derived. You can derive them by either looking at the net forces in the system or the energies. And if you look at the energies, you can find the Lagrangian. And if you get the Lagrangian, you can get the Euler-Lagrange equation. And if you get the Euler-Lagrange equation, you can do some algebra, take some derivatives, and then you'll end up with well, two derivatives, two second-order derivatives for both thetas. Theta 1, which is the angle in between the first rope and the first mass, and theta 2, which is the angle between the second rope and the second mass. And using those two second-order derivatives with respect to time, you could find everything else in the system and just model the motion of these pendulums. This GIF right here is an image, it's just a demonstration of three different double pendulums that all start at the same point with different initial lengths and different masses for the balls at the end. That's what I did with Julia today. This is kind of just an update video because there wasn't really anything crazy that happened today, and I just want to be making sure that I'm held accountable for continuing on the 66 days of data. So I encourage you guys to also follow along on the 66 days of data journey. And if you want to know more about double pendulums or see the derivation for these equations, then I have links to those in the description. Yeah, I'll see you guys later. It was a short video, but I didn't really have much to show today. Tomorrow there'll probably be more to talk about when I get really into Julia. But I had to do this homework assignment today and MATLAB failed me. Well, that's what happens. So I'll see you guys later. Subscribe if you want.